So today, and then also Tuesday, we're going to talk about groundwater. And today, we're basically going to talk a little bit of just some introductions to chemicals in the subsurface. Then we'll go through some very quick review of some groundwater basics. So some of you have had groundwater classes. This will be very reviewish. If you haven't, this will at least give you some idea about the terminology, but it's not obviously comprehensive treatment. And then we're going to think about chemicals in the subsurface. And we'll think about sort of three categories, what we call inert tracers, chemicals that don't interact with the subsurface, and they disperse in a way that tells us something about flow patterns and other properties of flow in the subsurface. Then we'll look at chemicals that interact with the subsurface that are inorganic. We'll talk about organic ones. Then I'm going to give you kind of an intro into organic contamination, which will then be the primary topic of next time, where we'll talk a lot about organic contamination as well as remediation. So that's just a reminder. We've talked about what the vadose zone and the saturated zone are for soils in the subsurface. And that was the topic of the last couple of lectures, at least part of it, where we're talking about soils. So now we're thinking about the kind of next step down beneath the land surface, where water gets into the saturated zone below the water table and starts to flow, and what the compositional attributes are of that, both from a natural perspective as well as a contaminated setting. So this is just kind of an infographic that summarizes some of what happens during that process. So these arrows represent advection, as we talked about last time, the motion of a material, in this case water, through the surface, from the air, obviously on the land surface, into the subsurface, and in this case into a body of water. And you can see kind of processes that go on, right? So there's partitioning, which is a term that chemists sometimes use to describe the sort of redistribution of materials between one phase and another. In this case, something, for instance, might be dissolved in water, and then it might decide to stick onto a soil particle. Or, as we'll see later today, and we'll talk about a lot tomorrow, we can also have chemicals that are not soluble in water that are applied accidentally to the land surface, that then, to some extent, they partition, they dissolve in water, they may volatilize again, and they may stick onto soil particles. We also have transformations that take place by organisms, especially once we get below the surface, but we can also have abiotic decomposition reactions, especially photochemical ones where light interacts with chemicals and changes them. Doesn't mean they go away, it might mean that they transform into something else, and more or less soluble, more or less volatile, whatever the case may be. Some component of that gets into the water, and then once the water starts flowing, it becomes transported. However, we can still have additional partitioning. We can have interaction between things that are dissolved in the water and the solid grains. We can have transformation, especially microorganisms can live in aquifers. And this term here, which will become important in a moment, I mentioned it last time, matrix diffusion, where whatever the characteristic of the substrate through which the water is flowing, sometimes called a matrix, sometimes called a substrate, the water will disperse, it will flow around the internal grains, and it tends to spread out composition, which can have the effect of diluting things. We can also, obviously, we've talked about this before, have all sorts of things that happen in bodies of water. So if whether stuff is discharging with contamination from the lake into from the groundwater into a lake, or it's flowing as runoff or what have you. But this is from the perspective of contaminants. You can see here, there's interactions that happen with the sediments, there's interactions that happen at the surface. There's also, in the case of organic contaminants, the possibility of making phases that sit on top of the water surface, like foams, which can trap other chemicals in them and so forth. I think we'll talk a little bit more about that next time. It's also useful to think about, well, how do they get into the subsurface in the first place? We've already talked about the difference between point source and dispersed, right? So these are all examples of point source contamination to the subsurface, things that are coming from a specific place. It could be a leaky underground storage tank. It could be a sludge lagoon on the surface. It could be contaminants that are ejected into a well deep beneath, the sort of layers which are typically sampled for water. accidental spills, leachate from landfill, leachates from homes. These are just some of the examples, but the important thing you'll note here is that all of these are producing plumes that are highest in concentration at the top, and then they're moving in the direction of water flow. So presumably water is flowing this way. We don't know about a third dimension. It could be flowing out at you, it could be flowing away, or it could be flowing in the plane. But this is what's called a permeable medium. And they've used sand and gravel there because that's a very permeable medium. Water can move really quickly through that. We'll talk about that in a second. Whereas when we get into the parts of the subsurface where the sort of bedrock, which water can still flow through, but much less slowly, what tends to determine how much contaminants that are introduced into this area will or won't flow and how much they'll disperse is more a function of the fracture pattern in the rocks. And this is something that's very common for us here in Hawaii, where we have some very dense rocks in our subsurface, but in some places they're very fractured. Much more difficult to determine water flow characteristics in fractured media than in porous media, but it's possible to do, and we'll look at a little bit how they do that in a second. So I also just want to introduce you the concept of, especially with organic contaminants, they're not all soluble in water. Now we're going to talk about non-aqueous phase liquids next time in a lot more detail, but this is an example of a plume of volatile organic carbon compounds. Okay, so these are low molecular weight, usually halogenated hydrocarbons and hydrocarbons that they're not very soluble in water, and they have a substantial volatility, so that they were sitting up here at the surface, they might be sort of slowly evaporating. But once they get introduced into the subsurface, they can interact with soil particles in various ways. So this is a pool of this stuff, and it's leaching into water tables, being distributed. And in some cases, these chemicals, we'll talk a little bit more next time, will float on top of the water table, or sometimes they'll sink beneath the water table, depending on if they're more or less dense than water. However, as they're flowing, they can also volatilize, and this volatile can come up and interact in the subsurface with water that's in the unsaturated zone, with the grains that are in the unsaturated zone, and with the pore spaces, and then migrate their way up into homes, for instance, and accumulate or not. And this is just an example of how this kind of contamination might be remediated. So here you can see a water table, and here you can see these organic contaminants sitting on top of them. So they're not dissolved in water because they're not particularly soluble in water, and they are fairly volatile. And so one thing that you can do is sort of drill a series of wells where you pump in gas, usually just oxygen or hydrogen, that we'll talk about next time, depending on if you want an oxygenated or aerobic environment. And then a series of wells that are used to sort of pull out the vapors that are contaminated. This works to take very contaminated places and pull them down a little bit. It's not going to completely remediate, clean up the whole area, but it's enough to sort of prevent this kind of thing from happening if the contamination is in a place where there's a lot of people. So we want to understand some of the physics of that before we get there. And I want to remind you that in general, organic chemicals in the subsurface, as well as inorganic chemicals, participate in this whole process that we've been talking about of soil formation, transformations between soil and living biota on the land surface and in the land surface, the formation of saprolite, and therefore the production of a soil horizon with a zone of accumulation, changes in pH, changes in organic matter content, reflect to some extent some of the other conditions that we've talked about, such as in the zone of accumulation, the precipitation of hydroxides and carbonates. Those will all those processes will affect the things that are in the through-flowing water that may end up getting down into the water table and getting into groundwater. And each place is a little bit different, but the sum total of a lot of processes are involved when chemicals are especially introduced on the land surface and manage to get their way into the water table. There can be all sorts of transformations and associations that we need to consider. Okay, so that was kind of the intro. Now I just want to talk a little bit about groundwater basics. So we've defined before the unsaturated and the saturated zone. They're shown here. This is like with depth down into a soil column. It's except for in very, very arid regions, these soil grains are usually at least wetted, meaning there's water kind of as a thin film around most of the grains. And so this is sometimes called the beta zone, this is sometimes called the phreatic zone by some people. But the point being that Here you have a non-interconnected web of water. Here you have an interconnected web of water. And depending on the characteristics of the subsurface and how much this transition from here to here changes, for instance, during the day or seasonally, you have a zone in between where water can be drawn up and sit at higher proportion of the pore spaces. It's still unsaturated, but it's not nearly as unsaturated as up here. That's called the capillary zone. And this is something that can, for contaminants that sit on the water table, for instance, the non-aqueous phase liquids, they can be dramatically affected by if this moves up and down, then those contaminants get pushed up and down with it, and they can interact with more surfaces in the subsurface, distributing that contaminant, more so in the subsurface. This is just, some other terminology, right? So the saturated zone, once we get below the water table, is officially groundwater, right? Whether or not it's in an aquifer or not, this slide here says, aquifer in kind of parentheses, depends on some other definitions which we'll talk about below. Just being in a saturated zone doesn't mean you're in an aquifer. You need to have some kind of impermeable boundary at the base of the aquifer, at least, that prevents water from continuing to flow downward. And in some cases, you can also have an impermeable layer on top. And this is just, another kind of, showing you another slide showing you what the nature of this capillary fringe is, which is basically a zone that can be, a centimeter to many centimeters. Okay, so these are some cross sections that help us understand aquifers a little bit. So the top curve is the land surface, right? It's kind of drawn in an exaggerated way. And we'll talk in a second about the physics of what causes the water table to follow the land surface, as opposed to just being a flat horizontal thing. But it's really a response to a couple of really fundamental forces, primarily gravity and height differences along the sort of land surface where atmospheric pressure is being applied. And so when water in the saturated zone, let's say this is determined by some kind of rock lithology, for instance, where that intersects the land surface, we could have discharge. And if this permeable layer that makes up the aquifer continue to go further down than that kind of area in the land surface that is allowing to discharge, then we wouldn't have discharge. And so again, you can have places where, because of variations in recharge throughout the course of the year, where this whole level goes up and down, we can have streams that flow or don't flow because of the intersection of the aquifer with the land surface. So this is, the definition between an unconfined and a confined aquifer. So you can see here that to have water sit relatively high up on the land surface, usually it's sitting in a permeable layer, but it's blocked from continuing to flow downward by something that's impermeable, right? And these can be different kinds of rock, crystalline rock, sedimentary rocks that have very fine grains that tend not to be as porous, much space between them, and we'll define that in a few slides coming up. But so this water that sits above that is in what's called a perched aquifer, that is unconfined at its top, but confined at its bottom. And again, if this happens to intersect the land surface, because this rock lithology in the subsurface, it has a different dip than the land surface, a shallower dip, and it can intersect the land surface, then we can get a spring there. This is what's called a confined aquifer, where water is sitting in between two impermeable layers, right? And so water doesn't come into this way. It comes in presumably wherever this structure intersects the land surface. And that's, again, very common for how what we have here in Hawaii. A lot of our recharge areas high up in the mountains along almost vertical structures formed by volcanic dikes take this kind of thing and move it more like this. And then it starts to flow along lava flow surfaces in the subsurface, and either comes out of springs, or we have the tunnels that have been dug and so forth. But the point being that the water beneath your feet doesn't necessarily come from right above you if it's in a confined aquifer. It flows for potentially some great distance. Okay, so this is another example that sort of shows you the difference between the aquifer, which, as you can see here, now we've got some rock types on here. Sandstone is a material made out of sand grains. It's relatively high permeability and high porosity. Shale, we've talked about before, is clay minerals that are packed together. It tends to be not nearly as permeable. So this is a confined aquifer. It's got these two impermeable layers. And it's sitting in a structure that looks like the letter U. That's called a syncline. And in this case, because the dip of the rock lithology in the subsurface has a different slope than the land surface, this syncline can intersect the land surface at some places and be covered by something else in other places. And so water can get into this layer by recharging in what's called that recharge area where the lithology hits the land surface and then flow down. The pressure of the water in here is essentially controlled by the relative elevation difference between this place and wherever we're sampling the water from. And that's basically the piezometric surface is the place of equilibrium of pressure where the difference between the amount of pressure that's in the water because of this height difference goes to zero. And if we sample or if we drill a well into this and where it's top at the land surface is below the piezometric surface, then water will flow out, right? But if we went to a place where this well was drilled at the same place, the piezometric surface, then it wouldn't flow out. We'd have to pump it, right? There's a hydraulic head that's pushing it, and that head is basically the difference between this surface and that surface. And we'll define that in a second. I also kind of want to remind you though that so as water comes in here in this recharge area, it interacts with the soil zone. There are chemical processes that go on there. One of the very common chemical processes that we can see is the addition of organic matter into the water that's percolating through, changes in pH. In some cases, we can see water get reducing. And then as it flows along down through this aquifer, it can change composition. If it enters into that system oxidized, because there isn't a ton of organic matter, it's not uncommon for as water flows in the subsurface to then get reduced and go down the redox ladder. So that elements like iron, for instance, become soluble. And if we're going to use that water for something like sample it for drinking water or whatever, first thing that has to happen is it gets reoxidized. You don't want to give a bunch of reduced iron to people in their households that will stain their sinks, for instance. And so all the stuff that we talked about earlier this week and last week are important in understanding the nature of groundwater compositions. And there's a couple of different things that can be monitored in groundwater. This is a couple of different types of wells. So these wells over here, you can hear this is basically, the unsaturated zone and the saturated zone. You can see a well that's drilled through here. And this thing called a bentonite seal is basically bentonite's a kind of clay that packs really tightly. So it's basically just an impermeable seal so that once you drill a hole, it doesn't spray out through the top. This well is unconfined along its entire boundary. It's just used to measure the water table, right? So you see these holes in the ground all over the place. Basically, the idea is that water is supposed to flow into them, and basically by putting a dipstick down, you can see how far below the land surface the water table is. This over here is a slightly different kind of well. You can see this confined until a specific place. So this one's at the bottom of the aquifer, this one's middle of the aquifer, this one's top of the aquifer. The bottom of the well is measuring, again, water, but not to measure the depth of the water, but the pressure in the water, which gives us an idea of the, whether or not we're at equilibrium or not, hydrostatic equilibrium, as well as how much flow and sampling of water is affecting the pressure in the water table. This is yet another well that is designed to sample water out of it. So that if you want to monitor, let's say that there's some chemical contaminant, you're trying to figure out, is it migrating, where is it migrating, at what rate? You drill a bunch of wells and you sample water out of them. And again, they have a permeable layer near their bottom, or at the depth that you want to sample, and then an impermeable layer and then encased the rest of the way up, so that you're only looking at water from a specific depth. And if you want to look at a bunch of different depths in one spot, you'll usually drill multiple wells so that you don't have to worry about dispersion or things that are happening within the well that might be affecting the distribution of chemicals in the substrate. Okay, so now let's just talk a little bit about the substrate that water flows through. So the two terms, I've been using them a lot, and sometimes I forget, they may not be intuitive. Some people may know these terms, some people may not, but porosity is officially defined as the percent volume relative to rock volume of pore spaces. So something that has a porosity of 50% has 50% grains and 50% spaces. Think about like your household sponge has a pretty high porosity. But porosity, it tells us about how much the space is, but it doesn't tell us if those spaces are connected with each other. That's what permeability tells us. Permeability is like a quantitative measure of how easy is it for water to flow through a rock. So you could imagine that you could have a relatively high porosity substance where all the pores are perfect spheres and those spheres don't interact with each other, the water's not going to flow through that. You can have a relatively low porosity thing where the pore spaces are elongated, and they are elongated in a way that there's an interconnected web. So we can have relatively high permeability even when the porosity is low, or vice versa. This is the thing that matters the most, the permeability in terms of determining groundwater flow rate and the dispersal of contaminants. So an important thing about permeability is that it doesn't have to be uniform in all directions, right? So we have something that we call an isotropic material, in which case the permeability is the same in all directions, right? Water can flow up or forward or backwards or to the side equally. But we can also have anisotropic media where, because of the material of the subsurface, for instance, the packing of the mineral grains or the fracture pattern within the rock, water has a preferred flow direction. So I try to show that here. This is like a shale where we've got all these clay minerals that are stacked very tightly. So water can flow along the planes of the clays, but it can't go perpendicular to them, right? So if water were trying to percolate in from above, it wouldn't be able to, because this material is impermeable to them in that direction. But if somehow water were flowing in from the side, where this rock lithology were rotated so that it's pointing its high flow rate direction towards the land surface, then water could get into it. And these are just two examples. You can have all sorts of other things, and the substrate doesn't have to, retain these properties as we move along. It can change, especially in response to other kinds of tectonic forcing, faulting, in the shallow subsurface, things that humans can do to the land surface, for instance. So related to permeability is yet another property, which is called hydraulic conductivity. Okay, and hydraulic conductivity is basically the speed through which water can travel in the subsurface. And it's basically related to a combination of porosity and permeability, and a third factor, which is how uniform are the size of the grains of the subsurface. So basically, if you take grains and you have small grains and coarse grains, even if the porosity is exactly the same, if the arrangement of them is the same, you're going to get a higher flow rate in this case than in this case. So average grain size in the subsurface affects the rate of flow, the hydraulic conductivity. Another thing that affects it is the sorting, right? So poorly sorted and well sorted, this means grains that are all of a uniform size and shape, and this means grains of a variety of sizes and shapes. So it turns out that the more poorly sorted, the lower the hydraulic conductivity in both these cases. So if we have big grains, but with a mixture of little grains that fill in some of those spaces between them, that lowers the hydraulic conductivity. If we have small grains and even small grains, that lowers the hydraulic conductivity. It's still true that if the average grain size is bigger, meaning this case relative to this case, we're going to get higher hydraulic conductivity. But the highest conductivity on this diagram is this stuff. Think about things like gravel, and lowest down here in this case. And these are just some values of hydraulic conductivity, just to give you an idea of how much they vary. So this is the hydraulic conductivity constant, which is just a measure of the rate of flow in centimeters per second or in gallons per day per foot squared, which is through a cross section. And remember, last time when we talked about the diffusion advection equation, we said we look at flow advection through a surface that is, at the edge of one of our boxes of, area in our control volume. So that's how this unit is being defined. This one here is centimeters cubed over centimeters per second, which is how it comes out, over centimeters squared, which is how it comes out to be centimeters. But the point being that you can see 10 to the minus 10 all the way up to 10 to the 2, right? So that's 12 orders of magnitude. That's 1,000 billion in terms of variation. And so you can see here, gravel has really high values. Sand has, relatively high values, but still slower by factors of 10. Silty sand means sand with finer silt-sized particles in between, which is sort of sand and gravel are basically like sand and gravel. Okay, and then silty sand is maybe one of these cases. Going on down into just silt, glacial till. This is something we obviously don't deal with it in Hawaii, but in places where there was large-scale glaciation as the glaciers go across the land surface to make a very fine rock powder that deposits in places. We find this, all over central North America, northern North America, and this lithology is very impermeable to water flowing through, as are sort of marine clays, right? So, the distances that water can travel in a second, you can just think about that, right? This is whatever, 10 to the 2, that's a meter per second. That's pretty fast, right? Whereas something like this, which is, down here in this, example, that's very, very slow. That water is going to move just a tiny little bit, very, very small fractions of a centimeter, even in a day. Okay, so water flow is driven by something called hydraulic head, which I alluded to before on the piezometric surface. And this is what hydraulic head, how it is defined. It is basically, a driving force for flow. And so this is the equation for it. You're not going to have to use this equation for everything. I just like you to know where it comes from. This term Z is the elevation, the difference between the zone of recharge of the aquifer and the place we're sampling it. So if we go into an aquifer, the aquifer is exactly the same, but we keep going deeper and deeper and deeper into the aquifer, and these other terms stay the same, then the head is going to go up because we're farther away from the zone of recharge, right? So the deeper we go, the more pressure it has. This term here, P over rho G, all of the variables are defined here. G is acceleration due to gravity. P is the density of the subsurface material, and D over here is going to be the flow velocity. So these two terms tell us something about the density of the subsurface and how the water within the pore spaces of that subsurface respond to forces of gravity, as well as the velocity field, the effective term for water, and how it responds to gravity. And you can kind of divide through or multiply through, in fact, by rho G to get a rearranged equation if you want to calculate the pressure. I haven't, taken pressure and pulled it over here and put this term over here. But if you want to calculate the pressure instead of the hydraulic head, you can do it either way. The key point being that if two things change, the hydraulic head and the pressure, which is with a driving force for flow in the subsurface, one of them is the depth beneath the piezometric surface, the Z, and the other one is what is the material of the subsurface? How dense is it? Is it really dense? Is it not so dense? Does it change as we go along an aquifer? That can change the response of the water in terms of the pressure because we're changing the lithology of the aquifer. So flow is calculated using something called Darcy's law, and Darcy's law has the exact same form as Fick's law, which we talked about last time. In this case, though, flow, which is given in the term Q for some reason, is a constant times the change in hydraulic head with distance along an aquifer, right? So if we don't have a change in hydraulic head along an aquifer, then we're not going to get any flow, right? That's one of the characteristics of this. K, this constant here, is the hydraulic conductivity, the thing that we just talked about back here on this slide. So somehow the ability of the subsurface to pass water through it, plus variations in the hydraulic head as we move along an aquifer, allows us to predict the rate of flow. And the rate of flow for us is going to be important because we want to understand the rate of dispersal of chemicals in the subsurface, especially contaminants. High or low is going to matter. Okay, so next thing we want to think about is, okay, we understand something about water. It can be characterized using all that stuff that we talked about. How do we learn how fast water flows? But then also, how do chemicals distribute in the subsurface? There's different categories of chemicals. Well, one category we call inert chemicals, sometimes called inert tracers. These are things that, for whatever reason, they don't interact with the solid particles, they don't volatilize, they don't chemically react away, they just move with the water. Think about it like a chemical dye that doesn't interact with anything. So you can actually inject it in one place and then put in some sampling wells in other places and look at the rate at which it shows up and the concentration at which it shows up, because processes of dilution and so forth can still affect inert chemicals, but that will tell us something about the flow field. What we're going to do is compare our non-inert chemicals, all the other stuff that gets put into the subsurface, and look at how their compositions change with distance along the flow field relative to the inert ones. And that will tell us something about the rate at which the physics of water flow is affecting dispersion and the rate of chemical interactions and biological interactions in the subsurface that are affecting concentrations in the subsurface for the non-inert things. So the idea with inert things is that we think of them as a tracer that tells us something about the rate of water flow. And there's a few different kinds of inert tracers. Not all tracers are inert in all systems, but there are enough of them out there that can be used to help define how this works in most of them. So let's look at an example. This is 2 wells, an injection well where this inert tracer is going to be put into the subsurface, and a sampling well, some distance downfield, down the flow field. It might be 100 meters, it might be a kilometer. But see all these layers here, A through G? These are layers with different lithologies and therefore different hydraulic conductivities, different permeability. They've been shown to be really extreme, right? Just to kind of help illustrate the point. So that up here, you know, all these layers in gray have somewhere in between the highest and the lowest permeability. And look at zone D. This one's got a high permeability, so water is flowing in this direction. We've injected something here at a single point in time, and for some reason in this particular layer, that stuff has moved really quickly to get to the well, whereas this stuff in the next layer down has moved very slowly, right? So that's telling us that we've got a high hydraulic conductivity layer above a low hydraulic conductivity layer. So now we look at a diagram. We just let this thing run. Maybe we let it run for months. Depends on obviously the distance between these 2 wells. And then we look at the time over which it took for water to get from one place to the other. What we see is that the layer D horizon got here to the well first, so it shows up first in time, and it makes a pretty high spike with a quick rise in concentration, not spread out too much in time. And we look at E, we see the opposite thing. We see that it has a lower concentration overall change, but that concentration is spread out over more time. We'll talk a little bit more about how that works out, but as it turns out, you can also have processes that cause these chemicals to disperse as they flow along their pathway, especially by interacting with grains. And then that dispersal process attenuates the flow of the chemical relative to the flow of water and gives us these kind of variable effects. And we see all these other layers in between E and D falling out somewhere in between, which tells us that if a contaminant gets into the subsurface, there may be certain horizons in the subsurface where it's preferred to flow very quickly and others where it's not. Okay, so now let's talk a little bit more about dispersion. I mentioned this last time as something that we can describe using fixed law and diffusion. There's a whole bunch of different ways dispersion happens in the subsurface, but these are 3 very common ways. These little yellow or orangey dots are meant to be grains in the subsurface. And these are really round, which would make this sort of an isotropic medium. Obviously, these grains don't have to be round, they can be flat. But if you have grains packed into your substrate material that aren't all at uniform distances from each other, so if the pore spaces are bigger or smaller, you can get different flow velocities through it, right? So water can go slower through the closer grains and faster through these. You can also have this long and short path, which is what I talked about last time, where water can take more time to flow through. And so therefore, these are the kinds of things that are cause variations like we saw in the last slide. And if your pore spaces are big enough, you can actually have areas of preferred flow in between the grains, and closer to the grain, friction starts to take over and the water doesn't flow as quickly. So what that means is that the farther and farther you go along a flow path, the more likely it is that these in combination with each other are going to slow down some of the water and not other parts of the water, which is going to cause dispersion of the chemical solutes in the water in the time domain, right? They're going to spread out over time when they arrive at the place that we're measuring them because of these differences. Now, this is like a plan view diagram. You're looking kind of down on an aquifer surface, and you've got sort of water flowing in 2 plumes side by side, a pink plume and a yellow plume. And they're encountering grains, and so obviously they can't flow through the grain, and water has to go around it. And this is another kind of dispersion. And you can see here that these two chemical plumes, just because of water not being able to flow through grains and has to flow around it, will eventually interact with each other and we can get zones of mixing. And so this is something that's of concern, especially in the lateral domain, where we may be in a very contaminated environment where there are multiple sources of contaminants, sometimes the same chemicals, sometimes different chemicals, where if we go far enough downfield in the flow direction, these two independent plumes can mix with each other. Sometimes that has other effects to change the distribution of chemicals in the subsurface. Okay, so how does that effect manifest itself? Those different kinds of dispersion. This is a diagram showing you basically, it's kind of depicted as a pipe, but it's an aquifer with presumably fairly laminar flow and unidirectional. So the water's flowing in on one side. Remember, Q is this term that comes from Darcy's law, and flowing out the other side. And then we're going to measure at various times, which equate to distances along the aquifer, the composition of chemicals, right? And so this is an inert chemical. It's not being reacted. There's no biology. There's no interaction with the solute. But you can see that its concentration is becoming fuzzier and fuzzier with time. And if you remember when we did the little sort of exercise during last class where I said, is this diffusion or advection? We'd say it's both, right? Advection is the moving of this spike of solute down through the aquifer, and diffusion is it's spreading out. And this is how it's manifested in a place. Like here's an injection well. This is a map. So there's a well, and then there's 3 wells downstream. One that's at closer, and 2 that are slightly farther away because they're at an angular distance. So a tracer is injected over a small period of time, and then it shows up at these other wells. And you can see that it gets to well 2 a little bit before well 3 and 4 because there's a slightly shorter distance, and so it arrives sooner than this one, and it's more dispersed at wells 3 and 4 because there's more of this kind of effect. That's what this is kind of trying to illustrate. The longer the distance at a constant rate of flow, the more dispersion is going to cause a chemical to disperse in the subsurface. Okay, so these are just some other examples, kind of just reminding you how the diffusion advection equation, which we talked about last time, applies in some simple scenarios. So this is, time 0, where contaminant is injected into the subsurface. This is basically, you're looking at a side view of an aquifer, and this is distance x along the aquifer. So we inject some chemical at time 0. And these are 4 different scenarios for different things that are happening in terms of this equation. So if somehow water could flow through that aquifer and not have that dispersion problem and go around grains, then pure advection would just transport this box to some distance downstream and it wouldn't have spread out at all, right? That's just pure advection. This case here is advection with dispersion. That's what gives us this kind of tailing spread out shape. This one here, where this other chemical, we don't know what it is, but it's some other chemical, shows up at a later time, it doesn't move as far in distance space as our inert chemical. There's something that's holding it back. We'll talk about this process in a second. It's called retardation. It implies that there's a chemical reaction between that aspect of the stuff that was injected and the particles in the ground surface, so that that stuff doesn't move as fast as the inert tracer, right? That is a process that's very important. There's another process. You can see how now here we've got this same peak. It's being held back, but it's also smaller. So let's say that while it's being held back, there's some kind of chemical reaction that's breaking that stuff down. So then, by comparing the characteristics of all sorts of different chemicals in the subsurface, and usually this isn't defined by just taking, an injection well and one well. There'll be an injection well and a whole bunch of wells. And then we can try to figure out, well, where's the peak concentration of each of our chemicals? How dispersed do they look? And do some chemicals look like they're moving more slowly than the inert tracers, or are some chemicals concentrations decreasing more rapidly than these? And that will tell us about this process of retardation and the process of chemical reaction, respectively. So everything, when we're kind of trying to quantify things in the subsurface, is done relative to the motion of the inert tracer. Okay, so The permeability effects on dispersion are strongest in non-isotropic media, as implied by the hydraulic conductivity and the permeability itself. And so we want to know something about the rock in the subsurface where there's a contamination as well as the water. So this is why, again, you'll oftentimes see people will be drilling wells and they'll take the rock that comes out of the well and inspect it and figure out, well, is all the rock uniform at depth, or are there variations in the textures of the rock, especially in terms of how they allow water to flow, because that's going to affect the dispersion of chemicals in the subsurface. Okay, so now let's talk a little bit about solutes that do interact with the substrate. There's a whole bunch of different interactions, but we've talked about all of these before. They are either acid-base reactions of the Bronsted type, Lewis acid, Lewis base, or ion exchange. Those are the kind of three primary things that happen on the particle surfaces of the substrate. And the substrate particles take charges just like the charges we've already talked about when we're talking about particles and estuaries. The difference is that now these particles are packed really close together. So for instance, this is an example where we're looking at distances along a flow path in miles. This is 50 miles along. And we're looking at the concentration of two things in the water. Dissolved calcium down here and dissolved sodium down here. And we can see here that the calcium concentration is going down and the sodium concentration is going up. So what's happening? Well, somehow the materials in the subsurface, presumably clay particles or other charged particles, are undergoing ion exchange where they're pulling calcium ions out of solution and liberating sodium ions into solution, right? And so we're getting a compositional change along the flow path. And this happens, all the time in the subsurface. But if we introduce a small amount of a cationic contaminant, think about like a radioisotope like cesium-137 or strontium-90, we want to understand relative to all the other trace metals that are in that solution, are they more likely to stick or not stick, which is also going to affect the rate of flow through this kind of chemical interaction. So I mentioned the particle charges. I just want to remind you of what they look like, right? If we have a plate particle with a negative charge, it can either have a single layer or a double layer model. For this set of examples, they just used the single layer model because it's easier to draw. But near the particle surface, because it's negatively charged, we pull in more cations than anions, right? And when we're out floating in the water, this is what allows colloids to stay suspended to their solvation. But in the subsurface, if the pore spaces are small enough that one particle surface and the particle surface on the other side of the pore space, like in this case, interact with each other, then these kind of charged solvation spheres around the surfaces can intersect with each other, and they can prevent some ions from flowing through. For instance, in this case, anions would be prevented from flowing through because of the way the charges are interacting with each other. Okay, so the next thing we have to think about is what is the chemical form of each of our things that might stick onto a surface and be retarded, move slower than the rate of water flow as a function of other chemical parameters, and one common chemical parameter is pH. So this is basically showing us the mole percent of each one of these chemicals that is bound to particle surfaces, right? So if something's 0% bound, it's going to flow with the water. And if it's 100% bound, it's stuck onto the surface, it's not going to flow with the water. And so you can see here that some elements, for instance, calcium, it is not bound all the way from these acidic pHs up to neutral, and then it starts to slowly become bound. Where something down here, like chromium +3, unless you're in very acidic medium, by the time you're at pH 5, it's basically 100% bound. So chromium will be separated from calcium as water flows through, let's say at a pH of 5 or 6, stuck and not stuck. And you can see where some of these other metals sit. And this is metals in the absence of organic chelating agents. If we add in organic chelating agents, we can move some of these curves around. It makes it even more complicated. Okay, so this concept of retardation is something that can be measured, okay? And retardation is related to two things. It is related to the effectiveness of binding of a chemical to a solid, meaning, for instance, not bound, bound, somewhere in between. The higher we are up on this side, the more retarded a chemical will be relative to water flow. So there's some kind of constant that measures that, and it can be defined as an equilibrium coefficient that we call a partitioning coefficient. So that, let's say we have, it doesn't matter what phases we have, but in our case, we're gonna have water and stuck to particle surfaces. So the relationship of any chemical A between being free in the water and being stuck to a particle surface is going to be defined at chemical equilibrium by an equilibrium constant. Obviously, water flow doesn't have to go slow enough to allow us to reach equilibrium, but this is the maximum distribution at any given condition. And if pH or something else is changing along a flow path to change this ratio, then we have to take that into account too. But this is something that we call a distribution coefficient that tells us the relative amount of stuff that's stuck between substrate and water. And it's usually written this way so that when this value of Kd, the equilibrium of distribution, is high, we've got a lot of stuff stuck to the substrate and a little bit in the water. And when this value is low, it's mostly in the water, not on the substrate. So this is the equation that tells us the relative velocity of a chemical A that is retarded relative to the velocity of water itself, right? And so you can see here's the velocity of water that we've measured with an inert tracer or some other method like a flow meter. And that divided by 1 over the density of the material on the subsurface, the porosity of the material, and this value Kd, the equilibrium constant of binding, is going to tell us the velocity of A. So for instance, for all things being equal, in the subsurface, these are characteristics of the subsurface. So if we're looking at a bunch of different chemicals, the only thing that can really change is this. And the bigger this value gets, the slower A gets, right? Because this is in the denominator. So this shows you how that works. And you can basically, because if we assume velocity is uniform along a flow path, the farther the distance we go, the more separation there will be between our retarded chemical and our inert tracer in the subsurface, the farther the distance is. Right. So this is an example showing you. This is an aquifer. We're flowing along from left to right, and tracer, the inert tracer, the thing that doesn't interact with the subsurface, is moving through a certain flow rate. And so this is at one time, and this is a later time. You can see that the tracer has moved farther along, and you can see that the chemical that's retarded has also moved farther along, but not nearly as much. And the separation between them is getting bigger and bigger. And that's because of this effect of retardation. The sticking on the particle surfaces in the subsurface is holding things back. And in the most simple case, you can look at the relative rate of retardation as being proportional to the distance that the water has flowed. So this is just an example of retardation in a sandstone aquifer for ammonium ions, for which, a distribution coefficient of about 2.4, a density of about 2.6, and a porosity of 28%. Just to show you how this works, we can say, well, what would be the relative velocity of ammonia relative to an inert tracer? And we can see it's about 4%, right? So for something, where it's not that well stuck, right? In this case, think back to what a distribution coefficient is. This is telling us that the ammonium is 2.4 times more likely to be stuck to the particle than not. And we have chemicals with KDs that go up to 10 or whatever. The flow rate is already only 4%. And so KD can have a really big effect on dispersion. There are other effects though as well, such as saturation of the subsurface, right? So if you just introduce a little bit of ammonia and it's got a favorable distribution coefficient, wants to stick on the particle surfaces, it will. But then if we keep introducing more ammonia and the particle surfaces are already coated with ammonia, then there's no more room at the end, right? That ammonia can't stick to those particles. It has to keep flowing down through the system until it finds a place where it can stick. And this is basically showing you what happens as we increase the volume of fluid measured in pore volumes, right? So if we have a cubic meter of subsurface and the subsurface is, whatever, let's say it has a porosity of 20%, then the pore volume is 20% of the total volume. That's all pore volume is. It's the amount of water that's in the pores. The more we increase the pore, the amount of water with that contaminant, the farther our contaminant is going to move, and the more dispersed it's going to be because it has to keep moving farther and farther and farther until it can find fresh substrate to stick onto. Okay, so this is the concept of relative retardation. This is looking at the retardation between two different chemical elements. So I've given you another example, a slightly different density and a slightly different porosity, higher porosity, lower density than the last example, just to kind of change up the numbers. And we put in a couple of elements, strontium and cesium, with their respective radioactive nuclide isotopes that we might find, for instance, in a power plant or a fuel processing facility. And you can see here that their difference in distribution is 10. And so we could go through and calculate the velocity of A relative to velocity for both of them, or we could, just put the equations over each other and see that they almost everything cancels out. And so, for instance, by calculating the velocity of this and the velocity of that, by plugging numbers into the equation and then ratioing them, we can see that their relative difference is velocity is 9.8, which is essentially the difference between their distribution coefficients, right? 10, 9.8, they're almost the same. There's another kind of interesting thing that you can think about, which is that in the subsurface, if we have a whole bunch of cations that want to stick onto things, they're going to interact with each other, and there's going to be some sort of pecking order where, because each one has its own selectivity coefficient, its own desire to stick onto surfaces, we really have to think about the competition between ions. And so if we're looking at just two ions in the subsurface, we can write out a coefficient where the relative amount of A and B ions sticking onto a solid or in the water are related by an equilibrium constant KAB. But we can also think about this relative to all the ions in solution. And the way we do that is to integrate this up. We say, well, instead of looking at the moles of this that's stuck in that, so water being in water or stuck, let's think of them as mole fractions. The moles of those things divided by the total moles in solution, which are shown here, for all the ions in solution. And then we can generalize this even further, which I'll do on the next slide, which is say, well, now instead of comparing A to B, let's just compare A to everything else in solution. And we derive yet another equation, which is for the amount of A that's stuck to a solid divided by all the ions in solution minus the amount of A that's stuck to the solid, meaning everything else that's stuck to the solid, is going to be some other distribution coefficient, A relative to the total, that's going to, that times the amount of A that's in solution and all the other things in solution. And if you think about it, this is basically the total dissolved solids over here, and this is the cation exchange capacity of a clay. So it gives us a way of predicting, in a relatively simple way. It may not give you the exact answer, but kind of a close answer of how much of any particular ion will stick onto a surface as a function of its propensity to stick onto the surface, right? Its equilibrium constant, as well as the TDS and the cation exchange capacity of the solution. Okay, so this is another example of how relative retardation looks. You're looking at an injection well, and you're looking at several elements: potassium, sodium, magnesium, calcium chloride. This is a relative concentration of 1, meaning the amount of concentration of solute measured at a sampling well is equal to the amount of solute measured at the injection well, after you've taken into account the dispersive effects, which are obviously going to spread things out in time and dilute them. But you integrate over the entire peak. And so now they've waited sort of several weeks, and you can see here that, for instance, chlorine, it runs through the system, and over time at the sampling well, it reaches a peak and it drops off again at about 1. So chlorine is behaving inertly in this system, right? We're getting back out of it what we thought we would get out of it. Some of these elements, especially magnesium and potassium, never quite reach 1, especially the potassium. It's because it has a higher selectivity coefficient for the solids. It sticks on the solids, it just doesn't flow through. The magnesium to a lesser extent. And we can see these elements, the calcium and the sodium, come up to higher values. The reason they're coming up to higher values is that as this water is flowing through and these things are being retarded because they're sticking onto the particle surface, these are being liberated. So we're getting extra concentration. Sort of like that concept of salting off that we talked about when fresh water enters into seawater and stuff comes off of particles. To retard one chemical, we have to liberate something else, right? We have to retain electrical neutrality in the subsurface. So this is, I have two slides that kind of show you the same thing. You're looking at plan view. There's a landfill up there. Water flow is moving from the top of the page to the bottom of the page. Each one of these dots is a little test well. And those test wells were drilled to define some control volumes, areas in the subsurface that were considered a reservoir. So this is one control volume, this is another control volume, this is another control volume. And you can see how they're defined by the wells, right? The wells are put in the direction of water flow. And so, for instance, comparing this set of dots to those set of dots is going to tell us about stuff that entered the box and exits the box. Comparing these dots to these dots is going to tell us about stuff going through this box. And then these dots along this one are telling us about flow along the direction of flow. And there's two things in here. There's contours for calcium and contours for ammonium. So this is one of these cases where the ammonium is being pulled onto the particles and calcium is being released. And so we can see that there's, in contour, the pinkish color is the ammonium. Its concentration is tightly controlled into a relatively small spot, but there's a plume of ammonium, and just like that example I showed you with multiple pore volumes, it will slowly migrate through the system, and there's a spike in calcium concentration that's moving faster through the system because it's being liberated to accommodate the ammonium. This is the same place, same setup. Now we're looking at the PE and the dissolved organic carbon content. Another thing that happens is water flows through the subsurface if there's organic matter in there, and if there's limited oxygen, which is typically the case in groundwater if we're far away from the recharge zone, the PE can go down, the iron can get reduced, et cetera, et cetera. And so we can see that as we move from cell 1 into cell 2, there's a change in the oxidation state, and we start to see an increase in dissolved organic carbon as particulate organic carbon is being decomposed in this landfill leachate. It might be part of what's driving down the low PE. It's liberated into solution. And all the ions, the things that are sparingly soluble, but that get complex by dissolved organic carbon, are going to be moved along in this system more effectively as a function of their association with the DOC, more so than because of their interaction with particle surfaces. And so this is where all these things that we've been talking about during the semester so far start to come to bear. Okay, so now if we think about organic chemicals on the subsurface, they behave a little bit differently, but they interact with particle surfaces through Lewis acid, Lewis base interactions. So things with a lot of functional groups on them, especially with a lot of oxygen, they may interact with particles more than others. This is kind of a hierarchy of how different functional groups interact with substrate. The highest being carboxyls or carboxylates if they are ionized, followed by alcohols, amines, thiols, aldehydes, ketones, esters, ethers, and then we've got unsaturated hydrocarbons, and then we've got halogenated hydrocarbons. These are some of the most gnarly contaminants that you deal with in the environment. We're going to talk a lot about halocarbons next time because they don't stick on the particle surfaces at all. They distribute really quickly in the subsurface. Whereas these kinds of chemicals, so think about like the humic acids and fulvic acids and simple low molecular weight fatty acids and so forth, these things like to stick onto particles. So this means highly retarded, not very retarded. And then we have a polyfunctional molecule with a whole bunch of things on it, maybe a bunch of these and these, then they're going to be really retarded in the subsurface. It may also be very reactive, biologically decomposed, but in terms of how they're held back, what they're composed of is a difference. So this is a diagram of the least retentive things, the halocarbons. So this is showing you the concentration of a molecule in water measured in parts per million. And this is the concentration that is stuck on the soil particles. Okay, and you can see a bunch of different lines, and these lines are for different forms of halogenated hydrocarbons. And these are all relatively simple ones. You can see here that this one ends in an ane, an ane, an ane, an ane. These are unsaturated hydrocarbons with, one carbon, 3 carbons, 2 carbons, and then different amounts of, in this case, chlorine versus bromine. There's chlorine. We get up into here, we have some enes, right? Some unsaturated molecules. And you'll notice a couple things about this. If you recall back when we talked about, we looked at zinc sticking onto clay particles, and we call those Langmuir isotherms, that the higher the concentration on any one of these lines of a solute in solution, the more of it is stuck to a particle, and that works here too. But because different of these chemicals have different selectivities, we get different slopes. So that if we had a contamination with a mixed group of halogenated hydrocarbons spilled into the environment, some of them, like this one, are not going to be very well stuck to the soil. We're going to have a low Kg for the soil. Others are going to have a really high Kg for the soil. So you can imagine some of these chemicals are going to distribute more effectively in the subsurface than others. And we can start to separate them from each other based on this kind of simple chemical equilibrium scenario, even though they're at the low end. This is another diagram showing you a similar thing. These are halogenated benzenes, right? So remember, we talked about benzenes as one of the family of BTEX chemicals, benzene, toluene, and ethylbenzene, which, toluene and ethylbenzene just have, a methyl or ethyl group stuck to that. But so if you add one chlorine onto a benzene, or two chlorines onto a benzene, or three or four, you will see that the halogens being added in does increase the binding of that chemical onto the solids. This is set up just like the last diagram. This is the concentration of the water in log units, and this is the concentration stuck onto the solids in log units. So that the more halogenated things are, the more they stick, basically. Okay, and so we can, for areas of specific substrate and solute, we can quantify the retention by making ourselves what's called a chromatographic column. And these are things that are done with kind of generic substrates in chemistry labs. Organic chemistry students do this all the time. That's how chemicals are separated in the lab, where you can look at the relative amount of retention by which chemicals flow through quickly and which ones flow through slowly. You can also do this in environments where you sample the specific substrate in your area and you pass a mixture of chemicals through it and just see how fast different things come. And this is sort of a hierarchy. It's very similar to what I gave you a couple of slides ago, showing you that hydrocarbons move through, with less retention, and the more polyfunctional or the more substituted they are, especially with oxygen-rich functional groups, the more retained they are. We can even have some chemicals, which we've talked about a little bit when we talked about organic chemistry. Remember, I talked about quaternary ammoniums. These are chemicals that have four things bonded to a nitrogen, which forces it to have a plus charge. These seem to be highly retained. These diquat and paraquat are two common pesticides that stick on the soil particles very effectively because of that charge that's on them. This is just a diagram showing you how chromatography kind of works. So basically, you can use chromatography in different ways. You can use it on liquids, you can use it on gases, but when you're looking at contaminants, what you will do is take the water that's contaminated, you'll heat it up into a vapor, and you'll flow it through a coil, which is full of a substrate, usually aluminum hydroxide beads, and different chemicals within it in that gas phase will stick to those particles to different effectivenesses. And then you have a little sensor at the end, which basically tells you when a chemical is coming through. And you put in a mixture of standards that you know what the chemicals are, and then you measure different things and compare it. So there's like, tap water, groundwater, and water from a very contaminated river or river water. If you look down to the details, you'll see here that basically this is at 25 degrees C. Things come through very, very quickly, and then you start heating the thing up at 2 degrees per minute to help make some of the more refractory chemicals start to migrate through. And then this is what comes through at 200 minutes. This is just water, basically air flowing through a substrate. And we don't know what the chemicals are in each of these peaks, but we compare them to standards. That's the simplest thing. The next thing you can do is you can have a gas chromatograph connected to a mass spec, which can look at the chemical composition of these things. It doesn't tell you the exact composition, it tells you the kind of fragments of material that might be present to help piece together specifics that are involved. Okay, so for the last few slides, I just want to go back now and talk a little bit more about groundwater contamination for organic chemicals. So that next time, we can delve into some more details. I want to remind you that we can have chemicals that are put onto the subsurface as point sources and dispersed. How they show up in groundwater is going to matter a lot as a function of how they were applied to the surfaces. We also have cases where we had accidental discharge and purposeful application. Oftentimes, purposeful application is discrete points in time that we know. Accidental discharge can either be a discrete period of time, a train wreck, or it could be something that's been happening over a long period of time, meaning next to a factory or something like that. But this is going to affect how contaminants get into the subsurface and how they disperse. The way things come out into the subsurface matters a lot. Also, do they get into the subsurface by coming from the land surface and leaching into the subsurface, or were they applied to the land in the subsurface? And the most common way for this to happen is kind of leaky subsurface storage tanks, as we've talked about before. This is just an example. This is, as I say, it's probably one of the most critical kinds of contamination that happen in the distributed sense in urban areas all around the world. It's not just like an American problem. It happens everywhere are gas stations, because these tanks, they're usually not very far below the subsurface, and they're not replaced very often, right? And if you have something that's been in the ground for 50 years, it's almost certainly going to crack. And about 20 years ago or so now, not quite, about 18 years ago, there was this chemical that was invented, this methyl tert-butyl ether, which is basically, it's an ether, it's got a single carbon over here, and if you do your little stick figures, that's a tert-butyl, tertiary butyl, because it's one carbon surrounded by 3 methyl groups, was added to gas. It was called formulated gas. It was first done in California to help make gas burn better so that it puts less hydrocarbon into the subsurface. And very quickly, within about 5 years, this chemical went from being completely unknown to being the most produced chemical in the world. Most produced chemical. And it was introduced and is used all over the place well before we understood anything about its toxicology, the way it behaves in the subsurface. And so that stuff is sitting in gas. Gas is sitting in these tanks, and these tanks are leaking all over the place. And so we have methyl tert-butyl ether contamination all over the place. And well, as I said, we'll talk about this. This is just an example of the kind of chemical that you could come in contact with very easily if you're sampling groundwater or drinking groundwater in an area anywhere near a gas station. So how do we know, well, how worried should I be, and how far is that stuff going to go? The things that we have to think about are the physical characteristics of groundwater flow, which we just went through. How retarded is that chemical, methyl tert-butyl ether, or anything else in that particular substrate? Does it have chemical or biological activity? Does it react with something? And does it dissolve in water? And is it volatile? Right? Especially for organic chemicals, these two components, and we're going to dissect this a lot more detail next time, have a big effect on their dispersion in the subsurface. So this is another kind of infographic-y thing that shows you, okay, here's the land surface, here's the top of the water table. An organic chemical gets introduced into the subsurface, what can happen to it? Well, it can get all the way down, dissolve into the water, and be ejected along, and because of dispersion, it can be diluted. We can have biological processes that degrade to some extent that chemical. We can have abiotic transformations, we can have sorption, and we can have volatilization, which is released back to the land surface. And all those things can affect that chemical. And so once we get to chemicals that aren't that soluble in water, we also have to think about what is their density. Are they more or less dense than water? Because if they don't dissolve in water, if they're less dense than water, they're going to sit on top of the water table. And if they're more dense than water, they're going to go below the water table. And again, these things, these what we call non-aqueous phase liquids, they can still be distributed by the groundwater flow that is pulled along with it. I have just a couple of other things that to remind you of, which is that the volatility of a chemical and the solubility of the chemical for organic chemicals are the two most important properties for understanding their dispersion in the subsurface. And these are just three different examples. These two are trichloroethylene. Now we talked about that at the end of last lecture. This is tetrachloroethylene. It's a slightly different chemical, but they're basically the same thing. Low retention, halogenated hydrocarbons that happen to not dissolve in water. They're a little bit denser than water, so they sit at the bottom of the water table. And so now you're looking at a plan view of two different chemical plumes, and this is a cross-section of a chemical plume showing you how this can distribute in the subsurface. And what we typically find with a lot of these organic chemicals that are sparingly soluble in water is that there'll be kind of two aspects of the distribution. There'll be a kind of a slow rate of flow that's in this case is heavier than water, so it's flowing beneath the water table, and it's sort of slowly migrating along at the rate of just like one or two buildings. But there's also some amount of it that is dissolved in the water, slowly dissolving, sparingly soluble, so we can get a much bigger zone with a low amount of contamination. It's just a fraction of that is flowing. And so, as I say, we're going to talk about all these things in a lot more detail, but I just wanted to get to this point to help illustrate for you that all of these variations that we're talking about become really realistic and important when we're trying to figure out, for instance, is that person's well water or that person's well water or both of them going to be contaminated by an organic contaminant that was introduced by an accident or on purpose or whatever, recently or a long time ago, and how do you figure it out? There's a lot of things you have to look at, but we have a checklist that you can go through and start to ask yourself some questions that will give you an idea of rates of migration, possible, fates of those chemicals in terms of reactivity and volatility and biodegradability, et cetera, et cetera. So we'll pick this up next time. Questions? Yep.
Ethanol free gas?
Ethanol free or ethanol?
Ethanol free or
So, I mean, ethanol is another thing that has been added to gas that one is not so much to make it burn cleaner, but it's kind of a nod to the farm industry to basically help them grow corn to produce ethanol. And so most gas until, I don't know, 10, 15 years ago was ethanol free. So ethanol was added to the gas to help it kind of go farther and not cost as much. It doesn't have very much impact. It burns at a pretty low temperature. So there isn't that much difference, especially because ethanol is one of these kind of very water soluble, non-retentive substances that breaks down in the subsurface. It doesn't really do very much.
it doesn't really make a difference.
Not really. I mean, it makes a difference to your car. Yeah. Now, I have a car that can use flex fuel, which means it can use higher amounts of ethanol. It's not all cars can handle it because it burns at a lower temperature. Uh-huh.